Hello, and welcome to my presentation. My name is Levin, and this summer I conducted research on the structural characteristics of garnet electrolytes for lithium-ion batteries under the mentorship of Dr. Levin. Alright, so let's begin. Lithium-ion batteries are the premier power source for current mobile electronic devices. They power our laptops, they power our phones, and they're poised to power the next generation of electric vehicles. Now, as such, a major area of research in material science is identifying materials that will make safer lithium-ion batteries. Just as in any other battery, lithium-ion batteries have a positive and negative electrode called the cathode and the anode. The battery is filled with a transport medium called an electrolyte, so that lithium ions carrying the battery's charge can move freely. When the battery is charged, the positively charged lithium ions pass from the cathode through to the anode where they are stored. Now when the battery is discharged, meaning energy is taken off the cell, the lithium ions move back to the cathode. And because the lithium ions are positively charged and they are moving, that creates a current which powers the electronic device. So currently the electrolytes in lithium-ion batteries are made of organic liquid compounds, which are very prone to leaking and combusting. The pictures at the bottom show only a few of the dangers involved with lithium-ion batteries. So in an effort to reduce the risk of liquid electrolytes, researchers have been trying to substitute them with solid-state materials which are far less flammable and lighter in weight. Now, as you can probably imagine, it's very difficult to find a rigid, solid material that can transmit matter as well as a liquid. That's why the choice of materials for solid-state electrolytes is so limited. And as of now, the two most prospective solid-state materials are lithium lanthanum zirconate and lithium lanthanum niobate, which belong to a class of crystals called garnets. These two materials have only recently been uncovered, and as of now, little information is known about how to properly synthesize them or what their structural composition is. In fact, no one yet knows what the exact distribution of lithium atoms in either material is, which is crucial for maximizing the lithium-ion conductivity in the batteries. So the focus of my project was to first identify the optimal processing routes for synthesizing phase-pure lithium lanthanum zirconate and lithium lanthanum niobate. Basically, I first had to find out how to make them. I then had to determine what factors stabilize the two materials in the cubic garnet structure as opposed to the tetragonal structure. And I had to do this because it's known that cubic garnets exhibit a much higher lithium-ion conductivity than tetragonal garnets. And when you're dealing with electrolytes, you want to have the highest lithium-ion conductivity for obvious reasons. Finally, I wanted to determine the exact distribution of lithium atoms in lithium lanthanum zirconate and lithium lanthanum niobate using a technique called reverse Monte Carlo analysis on neutron total scattering data, which I will go into shortly. So these were the three tasks at hand. Now, I keep referring to this term garnet. What is a garnet? Garnets are essentially just a class, a group of crystals that exhibit a very important characteristic, and that is that their structure consists of numerous gaps, open spaces, called interstices. The diagram on the right shows the garnet structure of lithium lanthanum zirconate, which is very similar to the one for lithium lanthanum niobate, without the lithium atoms. And as you can probably see, the oxygen and zirconate form a network of open channels, shown by the white spaces, through which lithium ions can pass through. That's why garnets are so prospective for solid-state electrolytes. They have these open spaces through which lithium ions can pass through. However, lithium atoms are required to support the garnet structure, and the illustration on the right shows the complete structure and how it would actually look like if lithium ions were inserted. Now, the lithium ions actually occupy the interstices, making it more difficult for lithium ions to pass through. Keep in mind that the yellow spheres representing the lithium atoms are only potential sites. This illustration doesn't actually describe how the lithium atoms are arranged. It just shows where they could be. Okay, so now I'd like to talk about the methods I used for the project. I first have to synthesize the lithium lanthanum zirconide and the lithium lanthanum niobate. To do this, I used a very popular technique called powder solid state synthesis, which is when you take the reagents in powder form, mix them, and then heat the mix. For the reagents for lithium lanthanum zirconide, I used lanthanum 203, zirconium oxide, and lithium carbonate. For lithium lanthanum niobate, I used lanthanum 203 as well, niobate 205, and also lithium carbonate. Now, the reason I'm using the lithium-7 isotope form of lithium lanthanum carbonate is because if I were just to take natural lithium, it would be a mix of the isotope 7 form of lithium and the isotope 6 form of lithium. And it's known that the isotope 6 lithium absorbs neutrons. Now, seeing that I'm planning to use neutron diffraction scattering later in my project, I needed to synthesize samples that would reflect the neutron beams rather than absorb them. Otherwise, my results would be inaccurate. So that's why I would have to use a pure lithium-7 isotope source so that my samples wouldn't absorb the neutron beams. Okay, so the first thing I would do is weigh the reagents in stoichiometry and then mix them with a mortar and pestle. To better activate the reagents, I later would mix them with a micronizing mill. And a micronizing mill is just a machine where you load your powder reagents into this canister filled with these solid cylinders, and you'd insert it into the micronizing mill, which would then shake the canister very vigorously, and because of that, the grinding between the cylinders and your powder reagents, you'd have a very fine mix. So then, after mixing the reagents, I would take the mixed reagents, press them into a pellet with a machine press, and then heat that pellet at temperatures ranging from 850 degrees Celsius to 1200 degrees Celsius to actually facilitate the reaction. And for both lithium lanthanum niobate and lithium lanthanum zirconide, I have to heat the samples at 850 degrees Celsius for 6 hours and then at 1200 degrees Celsius for 8 hours. So after heating the samples, heating the pellet, I confirmed whether the sample I synthesized was in fact phase pure lithium lanthanum zirconide or lithium lanthanum niobate by using a standard technique called X-ray diffraction. X-ray diffraction uses a machine called an X-ray diffractometer, which shoots a monochromatic, meaning a single wavelength, X-ray beam at your powder sample. Now, when the beam hits the sample, it is perfectly reflected by the atoms in your sample, and a detector then measures the intensity of the reflected beam. The X-ray diffractometer shoots the beam at multiple angles to produce a graph called an X-ray diffraction pattern, which is shown on the right. The x-axis of the X-ray diffraction pattern represents the angle of the X-ray beam, while the y-axis represents the intensity of the reflected X-ray beam. Using this information from the X-ray diffraction pattern, you can tell a lot about the geometry of your sample's atomic and crystal structure. Because we know the wavelength of the X-ray beam, and we know the angle of the incident beam, and we also know the intensity of the reflected beam, we can use an equation called Bragg's law to calculate the interatomic distances of the sample. And you can find Bragg's law at the bottom of the slide. Well, we can actually then compare the information and the X-ray diffraction pattern with information in known databases to determine exactly what material the sample is. So the X-ray diffraction portion of my project took up a bulk of the summer, and I'm going to talk to you about my results right now. I first tried to synthesize cubic lanthanum zirconide, and the first time I tried making it, I only mixed the reagents by hand with a mortar and pestle, and ended up getting terrible results because of this. As you can see, the fitted red model doesn't match well with my experimental data shown in black. In fact, the unaccounted peaks you see here circled actually indicate the formation of lanthanum zirconate oxide, which is incredibly stable. Once it forms on the sample, it's impossible to remove. Now, because I wanted to make phase pure samples, I needed to find a way to remove this lanthanum zirconate oxide phase. So, to actually prevent the formation of this phase, I started to use a micronizing mill in addition to mixing the samples with a mortar and pestle. Now, the results shown here came out a bit better than last time. As you can see, the fitted model matches very well with the experimental data. There's only one problem. The double splitting in the X-ray diffraction pattern, which you can see in the upper right hand corner, that's just a magnification of one of the peaks which has the double splitting, indicates that I formed the tetragonal phase of lithium lanthanum zirconide. Now, if you recall, I wanted to synthesize the cubic phase of this material, so I had to tweak the conditions even more. Well, alright, so I went back to the literature and discovered that researchers still don't know how to synthesize cubic phase pure lithium lanthanum zirconide. However, many researchers noted that it is possible to synthesize a very close structure to cubic lithium lanthanum zirconide by contaminating the samples with aluminum. And at first this puzzled me because I thought that if we're trying to synthesize lithium lanthanum zirconide, why would we want to, contaminate the samples with aluminum to get a completely different compound? Well, it turns out that if you just add aluminum to the sample, it will only substitute some of the lithium sites. So for the purposes of my research, it was perfectly fine to do so. So I added aluminum 203 to the samples, as many of the literature reported, and indeed I was able to obtain the cubic form of lithium lanthanum aluminum zirconate. As you can see from the X-ray diffraction pattern, the fitted model fits very well the experimental model, aside from a few unaccounted peaks which are circled that indicate the formation of trace amounts of lanthanum zirconate oxide. Fortunately, synthesizing cubic lithium lanthanum niobate turned out to be much more simpler than synthesizing lithium lanthanum zirconide. I only have to mix the reagents with a micronizing mill, heat them at the proper temperatures, and was immediately able to get it in the cubic phase. As you can see, the experimental data fits very nicely with the model in the X-ray diffraction pattern, with almost no amounts of the lanthanum zirconate oxide. So this was a pretty straightforward synthesis. Now, ultimately I want to use neutron total scattering to identify the exact distribution of lithium atoms in lithium lanthanum zirconate and lithium lanthanum niobate. Neutron total scattering is a very similar technique to X-ray diffraction, but a major difference is that some materials scatter neutrons better than X-rays, and that happens to be the case with lithium. In fact, lithium scatters neutrons 2,000 times better than it scatters X-rays. This means that we can tell significantly more about the arrangement of lithium atoms from looking at neutron diffraction data. Even more importantly, unlike in X-ray diffraction, where we only examine the peaks in the X-ray diffraction pattern, I will be using neutron total scattering, which takes into account the baseline as well, which often contains important details about the crystal structure. To analyze the neutron total scattering data, I will be using a technique called reverse Monte Carlo analysis, whereby adjusting the model until its parameters have the greatest consistency with the experimental data, I will be able to determine the exact distribution of lithium atoms in the samples. So, from the work I conducted this summer, I was able to conclude a number of things regarding the optimum synthesis routes for lithium lanthanum zirconide and lithium lanthanum niobate. The first thing I was able to conclude was that the synthesis of phase pure garnets from lithium carbonate is very challenging. As you probably saw when I was describing the results, it took many adjustments to the process to finally obtain phase pure cubic structures of the two materials. I also was able to conclude that to actually synthesize the materials requires very intimate mixing. And to do this, you really need to use a high energy ball milling to activate the reagents. If you just use a mortar and pestle and mix it by hand, it simply won't provide enough energy to the reagents to activate them. Also, I found that when forming these samples, numerous reactions compete with each other. For instance, the lanthanum zirconate oxide phase competes with the formation of the lanthanum zirconite phase, lithium lanthanum zirconite phase. And what we found was that heating at higher temperatures promotes the formation of other phases. So the optimal temperatures are below 850 degrees Celsius. I also found that lithium lanthanum niobate stabilizes at the cubic phase at room temperature, while lithium lanthanum zirconite stabilizes in the tetragonal phase. So to get lithium lanthanum zirconite in the cubic phase, I concluded that it is necessary to insert aluminum into the sample, and I used the 0.3 aluminum per formula to obtain lithium 6.1, aluminum 0.3, lanthanum 3, zirconium 2, oxygen 12. Now, I still see that a small fraction of other phases exist in my lithium lanthanum zirconite samples, so I still need to fine-tune the route to get the phase pure garnets. Currently, I'm working on this to prepare phase pure lithium lanthanum zirconite for neutron total scattering. As you recall, earlier I mentioned that I had difficulty removing the trace amounts of lanthanum zirconite oxide from the sample, so I still need to tweak the conditions a bit more. And in the future, I hope to obtain neutron total scattering data for both lithium lanthanum zirconite and lithium lanthanum niobate using the Los Alamos National Laboratory Neutron Diffractometer. And finally, I plan to perform reverse Monte Carlo analysis on the neutron total scattering data when I obtain it to determine the exact distribution of lithium atoms in lithium lanthanum zirconite and lithium lanthanum niobate. This concludes my presentation. I'd like to thank Dr. Leonid Bendersky for being my mentor and giving me so much support. I'd like to also thank Mr. Lee, Dr. Stone, Mr. Kern, and Mr. Savino for guiding me through the whole internship process. I'll now take any questions that the audience may have.